Watch. Thank you. Electrical forces. The same forces that make the winds blow, that makes a copper wire hold tight and strong, that makes water flow. All the forces except weak gravity, which helps the water, all the forces except nuclear forces, which weren't known a century ago, are electrical. Those were electrical forces of balloons gathering an electric charge, some extra electrons, or some electrons taken away, and then exerting forces. If you have two similar charges, same kind, both positive, they will push each other away like that. If you have unlike, positive and negative, they'll attract each other like that. I wish I could show you that, but you know it very well indeed. I want to show you instead the kind of patterns that we have, what we call electric fields. If we charge up these two objects, 1 plus, 1 minus, we can do that with an ancient machine, a Wimshurst. You may see Grandfather Wimshurst out in the corridor here. It will charge 1 positively, 1 negatively when we drive the plates round. And these threads, which I can just make suggestions to, will show you the directions of the electric field between a positive and a negative charge. And you can see how they curve like that, and even some of these up here curve up and over like that. We can move slightly closer together, and they join hands with some disaster. That shows the preparedness to make a force. The electric field ready to make forces on things is shown by patterns like that. We could, if you like, try charging both of them positively, but it will be a little disappointing. Would you like to see it? Well, we tried. Mr. Coates, can we try making both the same charge? There's a certain measure of caution necessary. You notice they go out like that, but between them there are buffers like that, buffers like that. These will go down and out there, and up and out there, and up and out there. It's not very easy to see the pattern. They certainly don't string across as they did before when they are like charges pushing each other apart. Thank you. Let us now look at an extreme case, not with round balls like these, but with a point. From a point, the field, electric field, is very hard and tough indeed. It will even drive a candle flame away. Watch the candle flame when we charge that point, which is just there. Can you see what used to be called the electric wind, blowing the candle flame away? Used actually for charging up the belt in my machine that we had with the balloon. The machine with the balloons is called a Van de Graaff machine. It's a modern version of the Wimshurst machine there, in which a belt is charged by charged things from points and carries the charge up into the big globe at the top. I would like you next to see how the electric wind can be put to use, clearing smoke from a chimney to decrease dangers of pollution. Mr. Coates is going to put up a tall chimney, and he will have to equip the chimney with smoke. I trust you are aware of the fact that there are people who smoke cigarettes. In this case, the machine is going to smoke a cigarette.
Okay, charge it.
We're going to pump smoke in. Can you see the smoke coming in? Fill it with smoke. Now a big, strong electric field between the central rod and the outside wires, and the smoke will clear away. Do it again, would you please? Lots of smoke, lots of smoke. Now clear it. That's actually used for clearing smoke from chimneys before it pollutes the outside atmosphere. I'm going now to show you an old experiment, which I think you'll find fun to see, of giving an electric charge to a real person. Mr. Coates, are you willing to endure this? He still has the spirit of Christmas with him. He's going to stand on an insulated stand, and now we'll give him electric charges. Kill it. Kill it. Oh. I may say Mr. Coates is aware of that. I charge him up again. Other hand. Leaky wooden rod. Okay. I would like to see if we can drive charges across from a candle. So we're going to use a flame of a candle where there's lots of chemistry going on, robbery of electrons from one atom to another, some gain, some lose. So there are many charged things in among the candle flame. We need a word for charged things. They will travel in an electric field. So they're called travelers, goers, in Greek ions. And we'll have here on the screen a note about ions which may be useful. We call them ions. There's no R in the name. They're groups of atoms or atoms which have become electrically charged by exchanging electrons. There's a great deal of trivial electron robbery goes on in good chemistry. A molecule, which is an atom group, or solitary atoms, can become ions by an electron being wrenched out of one into another who collects it up. Positive, negative. They'll both travel. Or a single atom. Or even sometimes now in a gas, if it's pumped down to low pressure, we may get electrons by themselves. Just, there's a strange spelling here for which I apologize. Quick. Here in the candle flame there are ions of both kinds, and we're going to apply an electric field between those plates and see what the ions will do. Can you see the candle flame bending to one way? It seems to be richer in one kind of ions. I've seen such flames divide into two, like a boy and a girl dancing suddenly fly apart to opposite directions because one has slapped the face of the other. When there's a spark, we remove the field. There is candle flame ions being carried across. But are they really electrified? Are they really electrically charged? We're going to show you in a minute with a special instrument. But first I want you to see a very old instrument. This used to be called a gold leaf electroscope. It has a metal leaf which is flimsy, and it isn't gold anymore. It's plastic coated with aluminium, and you behave. We're going to have that, and if you don't see it easily, you can see it on the monitors around the room, which will sometimes be helpful. I'm going to charge up from my huge 10,000 volt supply. I'm going to charge up the leaf and the support and see what happens. You ready? Right. Hold it. Now let's see if I can offer a flame with ions, as you know, to carry away the charge. We'll turn it the other way so that you can see it from another direction. Charge again. A match flame, very good way of removing electrification. Like that. I have here a very modern instrument. This is a micro ammeter here. There's a picture here on the screen. The micro ammeter has a tiny gauze cage, and in the center of it is a bright brass rod. If you look at the monitor, you may be able to see that in much greater detail. There's my finger in front of the rod obscuring the picture. I'm going to light a match and let the ions, the charged particles from the flame, flow in through the gauze. It's an open mesh, and let charge be carried across, because I've got a 9-volt battery, only 9 volts, between the cage and the central peg. Electronics, modern electronics, provides a very great amplification so that we can drive with that an ordinary milliammeter, thousandth of an amp, as a slave. The picture of it here is that 9 volts here will drive ions across, and that machine will drive a slave so that you're able to see currents as small as 3, 6, 9, 10, 11, and one more, a millionth of an amp. Now let's see what we can do with our micro ammeter with a flame. It's almost too much for it, wasn't it? Can you see when I blow ions in with my breath? Did it move? Didn't, all right. Move then. I can blow ions from outside in through the cage. Why do we bother to have something so sensitive as that? Because I have to be able to show you in the next lecture very small, safe quantities of radioactive material. This is a small radioactive source inside a tiny protective grid to keep it away from fingers or anything. And I'm going to bring it near, and can you see what the meter says? Multiplying by 1,000,000 times 1,000,000, something is making ions inside the cage. That's how radioactivity was discovered, and that's what it does. It makes ions in the air, in your skin, inside you, and inside certain kinds of reactor. So that we're going to talk about radioactivity next lecture, and I need to have a very delicate measuring machine which has a good slave to drive with the tiniest of currents of ions. They're perfectly real currents. I'm going to move from that to ions in water, which is where they were first known. Plain salt in water makes nice salty seawater with lots of ions in it. In this case, we're going to put zinc bromide in water, and you'll be able to see here on the screen a metal plate and another metal plate, and we're going to pass a current through zinc bromide solution from plate to plate. You will see the bromine, which you know already is an orange-yellow color. There it is. It's coming off here as a vapor or liquid and making a yellow solution in the water, and rather a dense one by the look of it. And here can you see the zinc is growing zinc crystals. You will see more and more fronds of crystal growing. I'd like to grow that for a bit, Mr. Coates, because it's a very nice picture to see. You are growing crystals. Atom after atom of zinc is losing its positive charges and becoming neutral zinc deposited on a crystal. Atom after atom of bromine is forming this strange yellow picture here. You can see the beginning of trees and ferns growing there. You see it even better on the monitor when my finger doesn't get in the way. Up there you have monitors that you can see by. Sorry. The next experiment that I want to try is to pass a current through water. Water by itself is a little difficult, so we put in a middleman merchant of sulfuric acid, and we have, you will see here, 2 plates. Again, you may see it better on a monitor. 2 plates with bubbles coming up from them. 1 set of bubbles hydrogen, 1 oxygen, and it's a method of manufacture, in fact. I'm going to let the mixed gases come out and do something very unusual and special. Mr. Coates, let's try it.
Ready?
No. I've got washing up liquid on my hand. Mr. Coates is blowing bubbles. Wake up your neighbour, say he's going to do it again. We have here a model of what is happening. You will have to be charitable with us at our beginning of it because we have to get it arranged. That's taut there, is it? Pull taut, pull tight and downwards a bit. Now, I've got to move yours to there. Now you're going to see on the screen our model. The model says there's metal plate at the left and at the right and air above, and now in the model you'll see how the 2 lots of ions move progressively along. No. That's as far as we can go. We'll turn it out and do it once more. Now we'll try to do it driven along like that. They're carrying the current. The poor fellows have to move extra fast when they get to the end because they find naked regions where the other kind of charge isn't there. Thank you. We are going to show you now another kind of ion, pure electrons let out into a vacuum by a boiling filament. We are going to boil them off a white-hot filament of solid tungsten. Mr. Coates, can you light up the filament, please? Now what's going to happen? We've got a lighted filament there, which some of you can see inside the glass globe. And with the arrangement that we have, is shown on the screen. We call this globe a diode tube. Diode means two pieces of metal, two terminals, two electrodes. One is the hot filament, heated so that electrons can get out more easily. The other is a plate where the electrons arrive with a bang. On they go through a milliammeter to show a current when you're driving it by some 30 volts. We'll try them both plus and minus according to the voltmeter there. Mr. Coates, will you turn on whatever voltage you have? Nothing happened. The voltmeter's reading. Nothing happened. Can you see it up there on the monitor? Mr. Coates, will you turn it round so that this audience can see it? Can you do that? No, it can't do it, all right. The only thing to do is to try sending a current the other way. Try to drive a current the other way. It's got a vacuum between the two things there inside the globe, and yet when you turn the current over the opposite way, drive it the opposite way, you get a large current. That's a current of electrons in a vacuum which have got out and have been driven by the electric field. It is, by its old name, a valve. It lets current through only one way. Nowadays, a diode like that can be as small as my fingernail very easily because it can be made with transistor or even finer new methods. I would like to show you a large piece of apparatus being used with an electron stream to draw graphs for you, to show you whatever you want to show as quick graphs by nimble electrons. We call it a cathode ray oscilloscope. There are a lot more such oscilloscopes round the outside here used by the people doing television recording. It's a standard instrument in modern engineering and science. And we're going to shoot a beam of electrons straight at the front screen. That's right. I'm sorry about the railway coming in. We're not going home by train. We are going to show you, however, a small train presently. We had to get it in. We are going to show you a beam of electrons making a bright spot, quite nice and bright, please, on a screen in the center of the face of the instrument. Can you see the spot up on the monitor over there? Now we're going to apply between two plates, above and below the electron stream, an electric field, positive and negative charges. See what happens when it goes on. Ready? On. Up goes the beam. Up. Off. On. Off. That's what happens when we connect a battery to two plates to drive the stream up or down. In this case, up. The next thing we'd like to try would be an alternating voltage, just a sample from the ordinary mains, please, Mr. Coates. Perhaps before you do that, you'd like to drive the spot across. We like to plot a graph against time, so we like to drive the spot across, time again and again and again. You do this when you read a book. You run your eyes across a line of print. Do you ever see the print going backwards when you get back to the next line? You have what is known in technology for this, reverse trace blanking in your brain. You blank out the signal until you get to the new line of print. Now that is happening here. The trace is going across from side to side, but not back. You don't see it. It's switched off for that. The next thing that we will do is to put an alternating voltage on that, please. Right. There's a slight change has to be made, so that we feed in a sample of alternating voltage, and then we see something which you can see on the screen here. There's a picture of an alternating voltage, up and down and up and down. The word time has got erased because I breathed on it by mistake. You ready, Mr. Coates? What? there is the pattern of the alternating voltage. You can see it on the monitor up there, and it will show you that the alternating voltage is going fully up and maximum and down to zero and down to maximum the other way and so on. Unfortunately, very unfortunately, my toy train won't run. It's made for DC, direct current, a plain battery. And in this house, at the moment, we're going to tell you we have only AC, only an alternating current. Mr. Coates is going to see whether the train will respond to an alternating current. There's a lamp connected between the rails. It hasn't been electrocuted yet. It's just showing brightness to show there is a voltage there. Train's not running. It doesn't like alternating supply. It doesn't like it. Can you hear the train complaining? Can you hear it? Slight buzz. It's complaining bitterly because the alternating current or an alternating voltage is saying to the train, go backwards, go forwards, go backwards, go forwards, go backwards, go forwards, 50 cycles a second. The train doesn't know what to do. But we can put a valve in. It's a rectifier, though in this case Mr. Coates will show it to you. It's a tiny, tiny little button between those two pegs where his finger's pointed. A little tiny button as small as my fingernail in the middle there. And that is a modern rectifier instead of the big diode tube. When he puts that together in the feed to the train, look what happens. That's better, thank you. Rescue the lamp from electrocution. Now let's look at the picture again. What is it that's happening there? The current through the train can go up and down, but not backwards. It's a one-way affair, so that you've got that. That's all you can get. What will you see on the oscilloscope on the Electron graph plotter now? Have a look at it and see what you expect to see and whether it is what you do see. You see it up there on the monitor. You notice how easily we use that as an easy apparatus that helps us in our work. One more thing I would like to try. Mr. Coates, I won't sing, I promise not to, but I will talk. Can we look now at the pattern, Mr. Coates, here? You ready? You'll be able to learn to talk French with a short U if you practice with this machine. We'll leave that for now, okay? Or you talk to it if you like. I'm going to go now to a large, crude, old oscilloscope and apply... I reversed order on you, I'm sorry. Okay. Now. Apply a force of a new kind. I have here a large magnet, and I'm going to apply the force with the magnet to the electron stream in this huge tube, rather like a picture tube.
That's fine.
Like that. We'll start the electron stream. There'll be a bright spot there, and then I'm going to bring the magnet up in a very strange way, along my arm, like this, sideways. And although it comes in sideways, although the electron stream is going long ways, it'll move the spot up and down. You see, a magnet on an electric current or a stream of electrons or any other charges acts crab fashion, like a crab on the seaside. You know, a crab is a strange creature. He's rather like certain kinds of politician. Faced with danger from above, he looks straight forward and runs sideways. Here is the spot on the screen. Can you see the spot up there? Yes. There's a nice spot on the screen. We are going to try a crab fashion force. The spot is due to electrons moving forward. The crab force is coming in along my arm with the magnet, but look, it carries it down. Turn the magnet round, what'll it do? You sure? like that. That kind of force is used in picture tubes because they prefer a magnetic field. I'm going to use this same supply for an illustration of what happens inside this kind of tube with a stream of electrons to paint graphs for you. It'll take a little time to arrange. It's going to be what I'll describe here on the screen. It's going to be a model of a stream of electrons in an oscilloscope. That's the name of a tube like this. It's to show anything oscillating, bouncing up and down. We'll have a water reservoir, a rubber tube, and the rubber tube is actually squeezed a little to say, please make a regular stream, and it's going to jet water out of a glass jet, and the water drops come out in a nice stream between two plates. It's as if I had a stream between two plates, my hands here, and I could spit water drops out. I won't actually do it. And if this one is charged positively, and this one is charged negatively, and if the drops of water coming out are charged negatively, they will stream out to one side. This will make a fairly watery mess of an experiment, and I'll go round and help. Here are the two plates, just here, that I'm holding. This is a charging ring to suggest to the water drops that they be charged. The water jet will come out in a moment. We'll take it out for a moment and then stop it again till we're ready. Sorry. No, we have to wait till it's ready. Too much. Now I'm going to let the water jet, various sizes of jet. We'll put our clamp back. Are you ready for your charging? We are. All right, we'll have to put back our clamp. There's the jet flowing. Now, can you see up on the monitor there what is happening? We are going to now charge up here the two plates and see if the stream moves. Is it charged up fully? Can you see it move? Now bring it back again, uncharged, charge up again. You must imagine the stream is full of water drops. You can charge it up to the full even if it hits the plate, doesn't matter. That's a model with water drops, and if you were a pigeon looking from above, you wouldn't see the parabola, you'd just see what looked like a straight line seen by looking straight down. But it's difficult to see that way, so we've arranged it like that for you. Thank you, Mr. Coates. It's taken some magic to get that to work, I can assure you. We're now going to make an illustration of the magnetic field and what it will do for you. I would like to have a piece of rope, please, and I would like to have a volunteer who doesn't mind being tied up. Come on. I took him on one side and told him what he must face before the lecture. Now, don't worry about the rope. You can take the rope in your hand. Please run straight across there. Don't hit the green cloth. Come back and run faster. Now, run straight across. Now we're going to tether him, but he doesn't know much about it. He doesn't know what's going to come to him. So we take this. You run back to there as before. That's the effect of the rope. For electrons, that's the effect of the magnetic field. Oh, you can keep the rope. We're going to show you that in a very difficult experiment because we'll have to darken the room very much. You'll have to sharpen your eyes. I have a globe with a vacuum here with an electron gun That's just a diode like that big globe you saw before with a hole in the plate, so the electrons, instead of hitting the plate, go right through and come out in an unending stream. So there's an electron gun firing electrons straight up. There's a screen at the end which will glow a little, and we hope it won't. And there is in here a tiny bit of gas, helium gas, which will show a strange color. So now we will try to fire up the gun. You may see it warming up a little bit. We are going to put a magnetic field on in this direction like that, not with this magnet, but with those two coils carrying current. It makes a more even field. And presently, I hope you will see a circular beam, a round orbit. Can you see a circular orbit? Still another kind of making of ions, making of charged particles. This is a nice electron stream which is coming straight out of an electron gun here. There's an electron gun there, and it's hitting a screen in front which will glow when anything hits it. Two things are going to hit it. The first thing which is going to hit it is the glow from the hot filament. We're going to heat up the filament, Mr. Coates, please, just the filament. It's on now?
On now, yes.
If you look at it on the monitor, can you see it glowing? A little difficult. You'll see it in the darker room now, I think, as a glow, and I'll turn it different ways and turn it different ways like that. And you see the filament is glowing, but much more important, can you see it's casting a shadow? Light does cast a shadow. It comes out of the electron gun instead of any electrons. And it's casting a shadow on the white front because there is in the middle of the tube a metal cross of that shape, a Maltese cross, which is there casting a nice good shadow for you to see. A nice good shadow like that and that. And now for that. We're now going to turn on the gun. We haven't applied any gun to the electron stream. It will make that screen at the end of the tube glow green. You can run the gun quite high voltage first, please. There, gorgeous green glow. Now what has happened here among the green glow which the electrons have made, except where they hit the metal cross, what has happened to the white one? Can anybody suggest how we could see both shadows at the same time? One word. The first letter is M. That's better. Where's my magnet? Now we'll have to look at it with less light and you'll see what happens. The magnet moves only the electrons. Light is moved by a magnet possibly, but very, very little, far too small for you ever to see. You can dim down the electron stream a little. Can you see the white shadow? And can you see the green part of it shifting when I shift with the magnet there? And so there is one of the old experiments in new form to show electrons moving in that direction. And if you know they move in that direction, you can work out which sign their charge is. They are negative electrons. And it's too late to change the arrangement of that. All engineers call the electrons negative and put the arrows on circuits the way positive charges would go round them. We are going to apply a large voltage to a tube which we pump the air out of. With it full of air, the voltage is not large enough to drive a spark, but we'll see what happens. Here's a glass tube with a side tube in the middle which goes to a pump. We are going to use a very violent little creature which raises to high voltage a high frequency current. We'll have a stimulation there. We shall want to show it to you in the dark. Not yet.
Non-pumping. Pumping now.
Now we're pumping out the air in this long tube. There's a spark, but a great big glow of a spark because it's going down to lower and lower pressure. If we could go fully low, we should see nothing there again. We should have pumped out so much of the air there's practically nothing left, only a stream of electrons. But we've changed color to a lower pressure. If I turn the tube to that audience and turn it to this, we're down now to a low pressure, and we cannot go lower without a different pump. That is just to illustrate the kind of glow that you manufacture and see in a neon sign, only it uses neon gas there instead of air. What is a spark? Why is it so noisy? That's just the expansion of gas when it gets hot. And why is it so violent? I'm going to illustrate a spark by assuming that you in the front row are atoms with electrons. Let me have one electron. Where's a spare one? There isn't one. All right, you have to do without. Sorry. I'm going to start here with one electron which is being driven by an electric field. Imagine that that wall is all negatively charged, a great wall of negative electricity, and that wall a great wall of positive electricity. So this electron is driven that way. First of all, we'll only have a little charge there and a little charge there, a small voltage between that wall and this one, small drive on this, weak field, and so this poor little electron says, well, he's repulsive, he's attractive, and I'll just dither along. Comes to a stop. And then he goes on. He came to a stop on him. And then he goes on, came to a stop. And on, came to a stop. And there he is. Now we'll have 1,000 times that, an enormous charge there, and so we're going to go crashing into the first one, take away his electron, crashing into the next one, crashing into the next one, take away their electron, take away their electron, all these crash into others, take electrons, and there's an enormous avalanche of electrons over there, and that can be picked up, for example, in a Geiger counter. We have another example of that, which needs very delicate arrangement. We have arranged on a sloping plank a set of glass marbles. These marbles are arranged in rows every so often at about the sort of space that molecules might be in air. And we're going to take one of them, and with magic we're charging it. And we're going to let it roll down from row to row to row in this artificial army and see what it would do if it's electric. Could it start by knocking an electron off the next marble down here? And that's all that happened. Nothing much happens. There isn't enough gravitational slope here, so we will push this up to a bigger slope. Now we try again. We'll push it up a little more. I'll hold it up. It's what electricians would call a leakage current. Now let's stop a trivial thing like that happening. This, instead of an electric field, has a gravitational field from that slope. Let's make it bigger and bigger. The camel's back is being strained. It's ready to break. The last straw will break the camel's back. We can just get away with it at this enormous tilt. And now you shall see a model of an electric spark. Ready? When we make sparks, colors come out. And if we stimulate instead the electrons of a solid like carbon, we can get from a white-hot solid a gorgeous collection of colors. The white light that comes out from a carbon arc by Mr. Coates there is going through a huge prism, very valuable one because of its size, and is going to make a band of colors here on the screen. We're going to make a very beautiful band of colors. I can't alter it. There is a spectrum, a delight to see. If you look at the monitors, you will notice that our television system does not find it easy to do yellow. It's for a very complicated technical reason, and we do not expect it. Yellow is anyway a very rare color. There's very little yellow just there in the spectrum. I'm going to mark with my finger where it is because I want you to look at another experiment in a moment where we have only yellow light from a sodium vapor lamp like a salted flame. Let's mark the yellow there. Can you do it without moving the prism? You can, all right. Presently, Mr. Coates will have replaced the white-hot carbon arc by a glass tube, or rather a quartz tube, containing sodium vapor. It's like a street lamp, but it's much more delicate. It isn't at high pressure. It gives out quite good, pure yellow light. How are you getting on, Mr. Coates? I can't see from where I am. That's all right. When we have done this, we're going to talk about the way in which we know what there is outside the sun. Here it is. If the lights go low enough, you'll see a yellow stripe just where my finger was, just there. That's pure yellow light. On the monitor, it will look an orange-red. That's part of our television system. The next experiment, and one of our last ones, is to take a sodium vapor, which is cool, not very cool, not far from 1,000 degrees on the centigrade scale, and pass through the cool sodium vapor, which will be made by this Bunsen burner here. This yellow light, when it does that, is just hot carbon. But when the sodium passes through that, when the sodium light passes through that, you will see the bright light from a small lamp, again like the big lamp that just made the spectrum. You will see the bright light casting a very strange shadow. Here's the Bunsen burner. There. Right. Okay. Now we're going to add sodium vapor to the Bunsen flame. When you do that, can you see? That looks like black smoke going up. Quite black, quite dark. You may even try it a little higher up in the flame, perhaps. No, still high. What?
Melting it.
Melting it? All right. Can you see a line of black smoke now? Up above the flame? Gollops of black smoke going flooding up. There it is. Now that happens with sodium in the sun's atmosphere outside the white-hot sun. The cooler sodium vapor picks up the yellow color and casts a black shadow. In the sun spectrum, you don't see all the colors of white light. A few colors are missing, very, very fine, sharply defined ones. They tell us what there is in the sun's atmosphere, what there is in the atmosphere of a very remote star or nebula, and in that way we know even that the universe is expanding. I'm going to show you an illustration of that. If you look at the spectrum of a remote star, you will see that the characteristic lines of, say, sodium are not in the yellow, they're in the orange or even red. They're shifted. And so we think that there is a tremendous motion. Let me now illustrate making waves. I'm going to move my pen like a moving atom here, and we are going to make a wave by moving the celluloid underneath. Now we'll have to begin further back. So sorry. We begin further back. Now ready? Like that. Now we do that. We're going to do it again now, and this time my pen is going to run away with me, away from the way the waves are going, and you'll see the wavelength, which is this distance here, from crest to crest, is going to be different. You ready? You see now the wavelength is enormously longer, nearer to the red, which has a characteristic longer wavelength. In that way, we think we live in an expanding universe. Well, it's not very surprising. If there were a great explosion once in some central place and pieces flying apart, is it surprising that the ones that flew out fastest have by now gone furthest? It isn't a case of why the mystery that the furthest ones are moving fastest. It's why the common sense that the fastest ones have got furthest. In conclusion, I'm going to remind you that the gas helium was discovered first on the sun. What? No. The gas helium was discovered on the sun and therefore was called helium after the sun. I'm going to drink up some helium from a balloon. This has been already filled with helium. And I'm going to recite to you, because in my mouth cavities, the vowel sounds are echoes to and fro with the speed of sound. But helium atoms move so much faster than air molecules that the echoes will happen much faster. It'll change the general nature of my voice. Just for fun, therefore, I shall say, 3 blind mice, see how they run. First of all, I'll unleash this. I want some oxygen for...
Three blind mice. See how they run.
Ready?
Three blind mice.
See how they run.
That's the end of the lecture.